Hi, everyone. I'm Max Resnick. I'm the head of research at Special Mechanisms Group, which is the part of Consensus where we work on things that are as close as possible to the chain. So we work on a lot of stuff related to MEV, transaction fee mechanism design, and this is joint work with my co-author Malesh, who's also at SMG and a professor at Rice University. So the basic idea of this paper is, one, I wanted to put the things that I've been tweeting about 1559 into a more formal notation. And the other one was basically to get this idea of modeling the fact that users are willing to wait, which actually was brought up in the last session in one of the questions. But major assumption of the current transaction fee mechanism design literature is that users arrive and then if they don't get in, they leave. Because that makes the results nicer. But in the real world, obviously, users may, in some cases, be willing to wait multiple blocks for inclusion if it means that they're going to get a lower fee. So obviously, we know there are some transactions that are time sensitive, like DEX trades obviously want to get in before the prices change. You might have payments in a physical coffee shop type setting where you probably don't want to wait for that to settle. That's probably quite inconvenient. You might be holding up the line, or you might have actions in real time or semi-real time games that need to get in quickly. But if we look at the chain, a lot of transactions are kind of simple transfers that are not time sensitive. There's stuff like L2 posting data, which is now through blobs on Ethereum, but this was happening a lot before that, where they would post, about 10 or 12% of Ethereum gas usage was L2s posting bulk transactions. And contract deployment, which if there's some devs here, you probably know that you should set some very aggressive savings parameters, and because you're deploying a large contract, you're going to pay a lot of gas, so you are willing to wait, quite a large amount of time to do that. And so you're going to set some parameters that allow you to wait sometimes up to a day to do that. So in this paper, we're going to analyze that specific setting where you have users who are willing to wait, and we're going to adopt this model of queuing and users who have time sensitivity, different time sensitivity from Huberman, Leshno, and Molemy, which considered the Bitcoin fee mechanism, and we're going to adapt it to situations where the block arrival process looks more like how it does in proof of stake than in proof of work, and to fee mechanisms that look more like the Ethereum fee mechanism EIP 1559 than the fee mechanism in Bitcoin. So our main results are, there's two results. One of them is about this transition from proof of stake networks to proof of work networks. We had the merge not too long ago in Ethereum, and that moved us from the static, or from proof of work block arrival, which is exponential, to a static block arrival setting. And so what was the effect of that on users? Well, we're going to claim that it lowered the amount that they have to pay in tips and lowered congestion. And then we're going to talk about this EIP 1559 result, which is when users are strategic and they're willing to delay in exchange for lower fees, the first price fee market and the 1559 fee market do not converge to the same price. In fact, 1559 has more revenue, so users are paying higher prices, and users who are less time sensitive are getting delayed longer. So the model that we use is, as I said, adapted from the classic Huberman et al. Paper, which considered Poisson arrival. And you have basically, the transactions are arriving according to a Poisson process with parameter lambda. And each transaction is associated with two types. One is theta V, one is theta C. Theta V is kind of the total value from landing the transaction. Theta C is the cost for each period of time that you have to wait for it to land. So theta c is really what we care about, which is measuring how time sensitive the user is. In their utility function, you see up there that their utility function is proportional. There's a negative theta c times w term. Negative your sensitivity times your wait time is there in the utility function, and that's what gives us this trade-off between latency and price. And we're going to assume that theta c is distributed according to f. So the other side of it, in queuing models, we have usually an arrival process and a service process. So this is the service process or the block arrival process. We're going to assume that the density of the block arrival process is given by this chi-squared distribution. You'll see why, because that seems kind of an odd choice to make. But if you set p equal to 1, you get the exponential arrival process, which is what we see kind of in proof of work. And if you do this limit, you can keep the ratio of p and u constant and send them to infinity, and you get this deterministic arrival process. So why did we make that choice? Just to make it a little more explicit, this is data from the week before the merge and the week after the merge in Ethereum. And you can see that before the merge, it was basically exponential. After the merge, it's almost entirely deterministic, except for like, maybe you can see there's one dot at 24 seconds there where that's like the missed slots, which is a pretty low number. So our first result is reframing of the result in Huberman et al., which is basically just a direct consequence of revenue equivalence that tells us what the equilibrium tip in the priority mechanism is. Maybe I should take a second to say what the priority mechanism is, which is what's used by Bitcoin. Basically, everything goes into a queue, and we take the transactions out of the queue that have the highest bids. And so basically, directly from revenue equivalence, we get this result, which is going to be useful for quantifying the difference between a static block arrival process and a exponential block arrival process. And a corollary is that we can get the wait time from the effective load. And just a small technical point is that we're kind of going to assume that theta v, which is the willingness to pay to get the transaction on chain, is high enough. In practice, it may be the case with this model that theta v is low enough such that the expected wait time is high enough that you don't want to participate, but we're going to assume that all users want to participate here. In some ways, you can just say, oh, we're just going to consider the set of users who have high enough theta v that the wait time doesn't push them out. So this is the theorem from Huberman et al. And basically, it says what the wait times and equilibrium bids are in the exponential case. So you can see it's clearly proportional to, the bid is clearly proportional to the wait time. We're going to show the same result that they show, but on deterministic wait times. And so you can see here, this is our theorem, which is showing the bids and wait times for the deterministic case. The subscript on the W here is 2. Why? Because that we're showing the results for blocks that contain 2 transactions. You can get analytic results in general for blocks that contain up to 4 transactions. After you go higher than that, there's a issue where you kind of run into some limits of Galois theory, and you don't have like a general formula for a quintic polynomial or higher, but below that you can get analytic results for k equals up to 4. So that's all the math, but let's look at the actual result in a way that's much simpler to see. Here you can see that in the exponential case, for k equals 1, the bids are higher and the wait times are longer. And in the k equals 2 case, the same is true. Basically, the punchline here is that when block arrival is unpredictable, you sometimes have blocks that come very quickly after the other, and probabilistically there's going to be less transactions in those blocks. So for example, if we have a Bitcoin block where the block arrival rate is on average 10 minutes, you sometimes have a block where one block happens and then another block happens 30 seconds afterwards. In that case, there's only 30 seconds for transactions to arrive, and that means on average that block is going to be much smaller than the average block. So that means that block is usually not utilized very well, and that leads to congestion. That congestion leads to this additional willingness to pay because you don't want to be delayed when you're high sensitivity. So now let me move on to the second point. This is basically going to start with a simple explanation of 1559. Ethereum blocks have a gas limit of 30 million gas, and they're going to target 15 million gas. The way they're going to get there is they're going to look at how many transactions are in them. If there's more transactions than 15 million gas, well, we're using more supply than we want to, so we're going to raise the price. On the other hand, if we're not using as much gas as we want, we're going to lower the price. And we're going to keep doing that just to give you an idea of what this is in terms of the actual parameters. If you have a full block, then you will go up by 1 plus 1/8 times the previous base fee. So your new base fee will be 1 plus 1/8 times the previous base fee. And if you have an empty block, it will be 1 minus 1/8 times the previous base fee, according to the parameters that are specified right now. So the idea is eventually we're going to converge to the right price because we're raising the price when we use too much and we're lowering the price when we don't use enough. But do we actually get there in practice? So here I basically plotted like a random sequence of 1,000 consecutive blocks. And I don't know if it was just kind of my personal like vendetta against 1559, but I was randomly choosing plots, and I think I found maybe the worst sequence of 1559 that I could have found on the third attempt. But the reason I'm showing you this is because it highlights the concern that we're talking about in the paper, which is there's a randomness in the arrival process of transactions, and that can fool the 1559 mechanism. And when the update parameter is too high, like I said, it's 1/8, which isn't necessarily optimized for anything, it's just what they chose at the time. You can have this rapid oscillation, and the rapid oscillation can cause bad effects down the line. And I guess like the reason that this particular graph looks so egregious is because the overall rate doesn't seem to be changing at all over the course of 1,000 blocks, which is 3.5 hours, but we have 32 spikes for no apparent reason. Unless there's some process where like every 3 minutes there's like a NFT mint going on that's spaced out over this period, which maybe it's the case, but like it seems to me this is basically just randomness in the arrival of transactions fooling the mechanism and making it spiky. And if you plot random stuff, you'll see like similar spikiness, but there might be some overall underlying trends that the mechanism is also picking up. But I thought this was like very clear in that it shows the spikiness without that. And just the order of magnitude here is from the baseline, which is like about 42 Gwei, up to the tallest spike is 70 Gwei. So we're like almost 66% of the base fee that we're increasing in a very short period. And it's not clear that that's actually corresponding to a change in underlying demand at all. So our model of 1559, we're going to do a simplified model so that we can try to get at this phenomenon. We're going to look at a version where there's two prices, high and low, and transactions are either high or low willingness to pay. And these are basically the results. Let me see if I can explain this as concisely as possible. Lambda H is the arrival density of high willingness to pay transactions. Lambda L is the arrival rate of low density transactions, low willingness to pay transactions. And you can see that the wait times, or the queue length, which corresponds to the wait time as well, is very different in these two. So if you're a low type transaction and the price is high, you have to wait for it to come down, right? And you're willing to do that because you're a low type. And if you're a high type and the price is high, you have to pay it because you can't wait for it to go down because you're high time sensitivity. And that causes some inefficiency, and it also causes revenue to be higher in our simulations. So there's some more results to come on this that we're actively working on, but I think just to remind everyone of the scene behind this, at the time that 1559 came out, gas fees were very high on Ethereum. And many people thought that that 1559 would lower prices outside the research community. In the research community, there was a lot of speculation that this would converge to the same price. What we're arguing is that if the parameter is set wrong, it might actually converge to a higher price and raise more revenue, which at the time that 1559 was kind of being debated probably was not what they wanted to do, because base fee or gas fees were already really high and the chain was almost unusable during like DeFi summer at the time. So some of the other things we talk about in the paper are ways to address this, an alternative mechanism using dynamic VCG, and simply just slowing down the update parameter for just to make it so that these spikes that I showed you happen less often. I'm all set. So I'm going to give everybody back 5 minutes.
And we have time for a few questions.
Oh, okay.
Very cool work. Quick question. Do you have a sense how much higher fees were because of the kind of lack of convergence that you're suggesting? Is it a small amount, a large amount?
So I guess like we're working on those results and we'll let you know, but in our model, we have this simplifying assumption that there's high or low willingness to pay. If you remember in these, revenue equivalence is basically telling you that it's kind of proportional to your wait time, but in your wait time, if you're high, is still very low under 1559, but if you're low, it's not as much. So I guess like the verdict is still out on that for like the practical sense, but it was a lot higher in our simulation. I think partly because we had this simplifying assumption where there's only high and low, and so when you go high and there's only low transactions in the queue, they don't make it in at all until it comes back down.
Like the server is on a random holiday. Low willingness to pay transactions, even if there's space for them in the block, they're just going to be left out. And in our simulation, like the top right of the left is saying that low willingness to pay transactions are going to wait 6 blocks on average, even though under a priority fee mechanism, that the load is so that they only have to wait like 2/3 of a block. High willingness to pay transactions see that and they say, if I pretend to be a low type, I'm going to have to wait 6 blocks. That's not worth it for me. But of course, it's the discreteness of our model that's pushing it up to 6. Just wanted to add that. Because stuff, at price, and the price will stay up. Price only goes down, and the block is really more model to answer your question.
Another intuition behind the revenue raising thing is basically if you're an airline and you squish everybody slightly more in economy, then they're willing to pay more in business. And so if you make the life for low type transactions much worse, then everybody who's semi-high time sensitive has to pay when the price is high and get in there. So like on this picture, like if you're at the 70 Gwei time and you're really time sensitive, you have to pay 70 Gwei, even though like that block was probably 10% full. And so the priority fee equilibrium price there would be much lower than 70 Gwei.
So the model you propose with the two dimensions where there's a theta v for my value of the transaction and a theta c for my cost of waiting, it seems like a very natural kind of model to solve in this dynamic settings. I really like the basic modeling approach. It's kind of curious in two different directions. So one is if my cost of waiting depends on what else happens in the meantime. So for example, I don't want to get front run. Does then tractability blow up? Is that become kind of an impossible case if my theta c depends on what else happens in the meanwhile? And then in the other direction, it's probably simpler, and I wonder if you get nice tractable expressions, is if theta c is just a depreciation rate on my theta v, so you kind of assume, basically take a two-dimensional model down to a one-dimensional model where my cost of delay is just a small fraction per unit time of my value of the transaction, sort of like a discount rate. Do you then get nice, intuitive, tractable expressions in that simpler case?
Wait, let me answer the first question, and then maybe you can repeat the second part. So the first part is like if you're trading on a AMM, you can do this thing where if you get in right away and you're like the first in the block, you can set an exact slippage tolerance, and there's no way for a sandwicher to come in and front run you. On the other hand, if you expect that you're going to get in two blocks, the price may change in the meantime. Now you have to set your slippage tolerance, the price that you're willing to accept, to accommodate the fact that the price may have changed a little bit. And even if the price didn't change, the sandwicher can come get you in that case. So like in some ways, even if you don't care about the trade going off immediately, but you just care about not getting sandwiched, you're still time sensitive in that case. Does that make sense?
It does, but even I think as long as there's any delay, there's some chance that something changes in the world that changes market prices. I sort of disagree with the part of your answer. That wasn't my question, but I disagree with the part of your answer where you say if you set a low enough slippage tolerance, you can protect yourself. I think that's wrong as long as there's a world external to the blockchain.
Yeah, if the price moves like a lot, even in the time between you submit and the time the next block comes, then there's still like a risk. But I'm saying like there's a natural tendency to want to get in quickly to not get sandwiched.
Yeah, and then the other direction is if your cost of delay is just a small linear fraction of the value of your transaction of your theta. So instead of a two-dimensional model, you have a one-dimensional model in effect. Mm-hmm. Do you then get nice tractable? You probably get a simpler characterization of equilibrium. I think that'd probably be interesting to.
Yeah, that might be a nice way to get at the idea here, where where was this? Basically, if users are not high enough theta v, I think that might be a nice way to get a similar result.
Yeah, it'll kind of make everything one-dimensional. If you're low theta v, you never trade. If you're high theta v, you trade right away.
Yeah, you get a nice cutoff.
You'll get a nice one-dimensional characterization, but in the dynamic setting, which is a little different.
That's interesting. Yeah.
Other work on.
Well, yeah, we'll take a look at that. Thanks.